In this section, we will be looking at quadratic equations, quadratic functions, and what it means to solve a quadratic equation and find its zeros, or x-intercepts. Some of you may have seen this in a previous algebra class, but we're going to go a little bit further and talk about some concepts like completing the square and equations that at first glance don't look like but are quadratic in disguise. You may remember that a quadratic equation is one that falls into this format where we have the variable x raised to the second power, and we have all of the variables in order from the highest power down. So we're starting with the x squared term, followed by the x to the first term, and then we have the constant c by itself without a variable. It's important to consider this additional stipulation that a cannot be equal to 0, because if this first term were not here, we would have what is considered to be a linear equation, because our variable would be raised to the first power, not to the second power. So we add that little additional caveat just to make sure that it's in fact a quadratic. The coefficients a, b, and c are all real numbers, and when our equation is written this way, we say that it's in standard form. If we use the special function notation f of x, we call this a quadratic function. It's still following the same pattern that we had in the last slide with the squared term first. And one of the things to consider is that when we find the solutions to the equation, those are considered to be the zeros of the equation, or where that graph crosses the x-axis, which is useful for us to determine what graphs look like. A quadratic function can have real numbers or imaginary numbers as those zeros or solutions. If I have real numbers as the solutions, that shows up in two different ways. One is that maybe if I have a parabola that's facing down, that means that the zeros are like this. These are real numbers that fall somewhere on the x-axis. And again, the way that this would happen would be that a, that first coefficient, is going to be less than 0. So the parabola is facing down. On the other side, if I had one that was maybe turned upward, where a is greater than 0, a is a positive number, again, I have some real number solutions that are crossing the x-axis. If the solutions are imaginary numbers, that means that the parabolas do not intersect the x-axis. So in this case, we have our maximum point below the x-axis, or in this case, I would have our minimum point being higher than the x-axis. That's what the graphs look like when there are imaginary solutions. We have a couple of different principles we'll use to solve quadratic equations, and the first is what we call the zero principle. It states that if I have two numbers, a and b, that are multiplied together and their product is equal to 0, then either a or b has to be equal to 0, or possibly both. What I have over here on the right hand side is just the exact same thing written in the reverse order, showing that either direction is true. As an example, let's consider the equation x squared plus 6x plus 8 equals 0. The way that we would typically solve this is to think about the factorization of this, what I can multiply each of these by to get to the product that I have there. I think that to get 8, I can do a plus 4 and a plus 2, and that'll get me to the plus 6x in the center. So now what I have are two numbers, even though they look more complicated, they're two binomials, multiplied together equaling 0. Let's call this one A, we'll call this one B. The zero principle says that either A has to be equal to 0, or B has to be equal to 0. In this first example, x would be negative 4, and in the second example, x would be negative 2. Notice that we end up with two solutions, and that matches up with the fact that the highest power that we had initially was raised to the second power. That's a theme that we'll see carrying through this section where we're trying to factor things completely. For a different example, let's look at 3x squared plus x minus 2 equals 0. Again, we can factor this into two separate binomials. Let's see, I just want to double check. That'll give me a plus 3 minus 2. Yeah, that gives me a plus 1x in the middle. Just wanted to double check that. So I have two numbers now that are multiplied together. This is one number, let's call it A. This is a second number, let's call it B. Two things multiplying together that equal 0. So either 3x minus 2 has to equal 0, or x plus 1 has to equal 0. Here we'll have 3x equaling 2, or x is 2/3. And over here we'll get x is equal to negative 1. Again, we're ending up with two solutions which matches up with the highest exponent of our original equation. Another principle we can use to solve quadratics is the principle of square roots. It's a lot of you kind of know that if I have, let's say, x squared equals 25, that would mean that x could either be equal to 5 or x could also be equal to negative 5, because if I take negative 5 and I square it, I will also get 25. Another way to think about this is that if I go back to this equation here and rewrite it as x squared minus 25 equals 0, this is a parabola facing up, which is shifted down 25 units. And so when I draw the parabola, the two places where this is going to cross the x-axis is here at negative 5 and also at positive 5. So that's really what those two solutions are telling us. Let's do a couple of examples. Let's look at 3x squared minus 21 equals 0. To use the square root principle, we want to move all of the numbers away from the x squared term so that we can take the square root of both sides. So I'll add 21 to both sides first. Then I'll divide by 3. And then I'll take the square root. So I'll get that x is either equal to positive square root 7 or x is equal to negative square root 7. Again, I'm ending up with two different solutions, and that matches the square that I have as the exponent. Let's look at another example. Let's look at 5x squared plus 10 equals 0. We'll subtract 10 from both sides. Then we'll divide by 5. And then we'll take the square root of both sides. When I take the square root of both sides, I'll get that x is equal to the positive square root of negative 2, or x is equal to the negative square root of negative 2. We learned last week that when we have a square root of a negative number, that is actually an imaginary number. So this will be x equals the square root of 2 times I, or x equals the negative square root of 2 times I. Notice I'm taking that negative out from underneath the radical symbol and putting it instead as I, because the square root of -1 is equal to I. That was kind of our little thing we did last week. All right, this third example is called completing the square, and it may be one that you're not familiar with, but we'll be using it going forward when we look at some of our more complicated functions later when we get to conic sections. The steps are written here, and I'm going to go through a couple of examples to show you how each of the steps work. All right, let's consider 2x squared plus 12x plus 10 equals 0. We could try to factor this and then use the zero principle. Sometimes factoring gets to be a little bit complex, especially when the numbers get larger. And the square root principle usually works only when there are two terms. And because we have a middle term with an x in it, that square root principle isn't going to work. Though what we're going to do is modify this so that we can use a square root principle. So step one is to get only the variables on one side and everything else on the other. So we're going to get variables on one side. So I will subtract the 10 from both sides. The next thing that I want to do is I want to remove any coefficient that's in front of the x squared. So there's a 2 that's sitting here, but I'm going to factor it out of both of the x terms. So we're going to divide both of those terms by the coefficient that's in front of the x squared term. So on the left-hand side, we'll take the 2 out into the front. We'll have x squared plus 6x, leave a little bit of space there. And we'll just leave the -10 on the other side. We'll just leave that alone. Now this is the completing the square part. And it comes from the idea that when I have a perfect square, which would be the same thing multiplied by itself. The process I can use to multiply this out is the first terms are going to get squared. The last terms are going to be squared. And then to get the middle term, I'm going to take these two, which is 5x, and I'm going to take these two, which is another 5x. So I'm taking those two terms multiplied together. Another way of thinking about this is I'm taking these two things, multiplying together, and then doubling, plus 10x. So it's that multiplying the two terms together and doubling that gets to the middle term. Back here, the middle term is given to us, so we're going to go in the opposite direction. We're going to take half of this term here, and then we're going to square that and add it into this space right here. So half of 6 would be 3. If I square 3, that would be 9. So I'm going to add 9 right here. Again, I take half of the middle term, which is 3. I'm looking just at the coefficient only. And then I square that number and I add it in over here. That's called completing the square. And I'll show you why we call that in a minute. We need to remember, though, that I've added a number onto the left-hand side, and to keep my equation balanced, I have to add something to the right-hand side to balance it out. Now, it looks like we added a 9, but really, that 9 is being multiplied by this 2 on the outside, so really what we added overall was an 18. So I'll add 18 to the right-hand side to keep the whole equation balanced. Looking back at what I have in parentheses on the left, the 2 is still hanging out here, and the square that I have created by adding that 9 ends up being whatever I found for the middle term here that's the number that'll show up. X plus 3, the quantity squared. If I multiplied this out, I'd get x squared, I'd get 9, and then these two multiplied together and doubled gets me the plus 6x. Right? So I'm just verifying that how I'm breaking this down is in fact what I had above. On the right-hand side, what do we have? We've got a plus 8. Okay. So this step was completing the square. And balance both sides. Now let's divide both sides by 2. So we have x plus 3, the quantity squared, is equal to 4. And then I'll take the square root of both sides. Now I'm going to be able to use that square root principle. When I have something squared and I take its square root, I end up with just the item that's under the radical, so I'm going to have an x plus 3 here. And when I take the square root of 4, I have two options, right? I have either plus 2 or minus 2. So x plus 3 is either equal to 2 or x plus 3 is equal to negative 2. That gives me x equals a negative 1 or x equals a negative 5. Again, I end up with two solutions, and that matches up with the fact that I had something raised to the second power originally. Let's do one more example of completing the square. X squared minus 10x minus 22 equals 0. This is one, in fact, that doesn't factor very easily, because the only way that we can get to 22 is 2 times 11 or 1 times 22, and neither of those are going to get us to that 10 in the middle. So this one isn't factorable. So what we'll do as our first step is we'll move the 22 to the right-hand side. Then if there's a coefficient in front of the x squared, we factor it out, but there isn't in this case. So what we'll do is we will complete the square here. We look at that middle term, which is a 10. You take half of that, which is 5, and then square that. So we'll add in a plus 25 here. And to keep the whole equation balanced, I'll add a plus 25 here as well. What I've created on the left-hand side can be collapsed into x minus 5, the quantity squared. The sign will stay the same, and this number is going to come from half of this number. On the right-hand side, it looks like I've got 47. Now I'll take the square root of both sides. And I know that I'm going to get either the positive or the negative as an answer. So x minus 5 is either equal to positive square root of 47, or x minus 5 is equal to the negative square root of 47. Add 5 so that we can have the x on its own. And we end up with our two answers. The quadratic formula is one of the ways that students are most familiar with solving quadratic equations. And if you know it and have memorized it, it's good to know it works all the time. The completing the square works all the time, and so does quadratic formula. Sometimes, though, when you use the completing the square, it creates fractions and it can get a little bit messy. And especially if you have decimals in your equation, like you do often with application problems, the completing the square gets difficult to manage. So the quadratic formula is a tried and true method that works a lot of the time on every problem. So let's do an example here. Let's look at 3x squared plus 6 equals 10x. To use the quadratic equation, we need to have all of the terms on the left-hand side or on one side of the equation and 0 on the other. And it's important that we put the terms in order with the squared term first, the x to the first power second, and the coefficient third, so that we can properly identify a, in this case is 3, b in this case is negative 10, and c in this case is 6. So plugging these items into the formula here, we're going to have that x is equal to negative b, so that'll be a negative 10, right? The opposite of whatever the number is for b. Plus or minus, that plus or minus is how we end up getting two different answers. B squared, that'll be negative 10 squared. Reminder, just a little side note over here. Negative 10 squared is not equal to negative 10 squared with parentheses. Order of operations tells us that we have to square the item that's directly next to it. So the one on the left, we square the 10 to get 100, and the negative still stays there. On the right-hand side, order of operations tells us that we square whatever's right next to it, and that's everything in the parentheses. So we end up with negative 10 times negative 10, which is 100. So these are not the same. So it's important if you're using a calculator to remember to type that in so that that b squared is always going to be positive. All right, minus 4 times a times c all over 2 times a. So I'm getting 10 plus or minus just double check that. 100 minus 4 times 3 times 6. Yeah, that's 28. And then divided by 6. 28 is 4 times 7. So that'll end up being 2 times the square root of 7. So we have that x is equal to 10 plus or minus 2 times the square root of 7 over, got to plug in my calculator or computer, over 6. When you have a fraction with two different terms in the numerator that can be simplified, we have to remember that we can't cancel with 1. We've got to actually split it up. That 6 has to be divided into the 10 and also into the 2. So 10 goes into 6. I think everything is divisible by 2, right? That would be the greatest common factor. So we can say that x is equal to 5 plus or minus the square root of 7 divided by 3. I just divided all three terms by 2. And these are my two answers. One is the plus and one is the minus in the middle of the 5 and the square root of 7. All right, let's do one more example like that. let's look at x squared plus x plus 2 equals 0. Again, this is one that we can't factor because the only way that we can multiply two numbers to get 2 is 1 times 2. And those are, when we combine them, it's going to be a 3 because they're both positive, or -1 and -2. And that's not going to get us to a 1 here in the middle. It's going to get us a +3 or a -3. All right, in this case, A is equal to 1, B is also equal to 1, and C is equal to 2. So x is going to be equal to the square root of b squared, that'll be 1 squared, plus, oops, that's wrong, negative b, skipped a step there, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Underneath the radical sign, I'm going to have 1 minus 8, which is a -7. That's going to end up being an imaginary number, right? So -7 under the square root, that's the same as square root of 7 times I. So our two solutions are x equals -1/2, that's the real part, plus the square root of 7 over 2i, or x is equal to -1/2 minus square root of 7 over 2i. Two solutions, they're both complex numbers, and we know that that means that in this particular case, the graph is not crossing the x-axis. The discriminant is the part of the quadratic formula that is underneath the radical symbol. And if we end up getting the discriminant equaling 0, that means that we're going to end up with only one solution. If there's, maybe if we had, let's say, 3 plus or minus the square root of 0 over 6. Because this 0 is going to go away, we just end up with the plus or minus becomes irrelevant, and we end up with only one solution. In the one solution case, that's where the graph, in this case, x would be at 1/2. In that case, the graph is touching the axis right at 1/2, and so we end up not having two zeros, but we have one, and it's doubled up. It's called a multiplicity, and we'll talk about that in a couple sections from now. The example that we just saw was the second one where we got, or the first example that we did was where we had a real number greater than 0, and we had two zeros. And then the third one is the last example we did where we had the discriminant less than 0, and we had complex numbers, complex conjugates in fact, where the two numbers are identical, but the only thing that's different is the plus and minus in the middle of them. All right, these problems are looking at equations that don't look like quadratics, but we can use some of the methods that we know about quadratics to solve them or reduce them. In this first example, we see something that's raised to the 4th power. And what we do is we make a substitution so that we can rewrite it in the same format, but instead of using the x squared as the variable, which usually comes from the middle term, we're going to use the variable u. So then that x to the 4th power becomes u squared, and then we can use factoring or quadratic formula or completing the square. We can use any of the methods that we have before to solve. So let's do some examples. I forgot to put some space in here, so let me make some. Okay. Let's look at x, oops, come back, x to the fourth minus 3x squared plus 2 equals 0. This is something raised to the fourth power, so up until now we haven't learned how to do this. The key that we use is to look at the middle term and we use a variable change. We're going to say let the variable u be equal to x squared. If I square both sides of this, I would have that u squared is equal to u to the fourth, or sorry, x to the fourth. Just squaring both sides there. So instead of writing x to the fourth, I'll write u squared. Instead of writing x squared, I'll write u. And the number that doesn't have any variables, we can just leave that as it is. Well, I know how to solve this equation. I can factor this into, let's see, u minus 2 and u minus 1. So I've got u minus 2 equals 0, or u minus 1 equals 0. But remember that we had this variable change up here. So really, instead of writing u, I should write that x squared minus 2 is equal to 0, or x squared minus 1 is equal to 0. My original equation had 4, was raised to the fourth power, so I know I should end up with 4 solutions. Let's add 2 to both sides in this first equation. X squared is equal to 2. Taking the square root of both sides, I'll get that x is equal either to positive 2, or positive square root of 2, or negative square root of 2. For the next equation, I have that x squared is equal to 1. And again, take the square root of both sides, and I get that x is equal to either the positive or negative square root of 1, which is just 1. So my 4 solutions are 1, negative 1, square root of 2, or negative square root of 2. Look at an application problem that uses some of the ideas we've been talking about today. A ball is thrown across a playing field from a height of 5 feet above the ground. That 5 feet is represented here. It's a pretty bad picture. At an angle of 45 degrees to the horizontal. So what they're saying there is that if I had a horizontal line that was drawn here, this angle is going to be 45 degrees. It's created there. And the speed is at 20 feet per second. So using some physics, they put this formula together for us. You can see that the speed is represented in the denominator of that first fraction. The 5, which is the height of the ground, is at the end. And then the 32 represents the gravitational pull. We have 2 things we're trying to find out. We're trying to find the maximum height that the ball attains. So at the top of the parabola, what's that height? And then we're also trying to figure out how far the ball is going to travel, right, before it hits the ground here. So we want to know what that distance is. These are 2 problems that are going to use the idea of completing the square and the second one is going to use the quadratic formula. So let's look at the first one. This equation is a little bit complicated, but we'll just tackle it one step at a time. I'm going to rewrite the equation here. Y equals negative 32 over, let's write that as 400. And I think we can actually simplify that fraction there. Let's simplify that. Grab a calculator. This is a big calculator problem, so you want to grab a calculator if you have one. That we can simplify to 2 over 25. Oops, I don't need to do that yet. Okay. So when we use the process of completing the square, what we do is we put the two terms that have x's together. Oops. But we have to factor out that coefficient that's in the front. And when we do that, we're dividing the x by that fraction, and so that's the same as multiplying by the reciprocal. So what we end up having is a negative 25 over 2. The plus 5 goes out here, just to kind of verify our thinking. If I took this fraction in the front and multiply it by both of these, the two fractions are going to cancel and I'll end up with that positive x that I had up here. So I'm just wanting to verify that when I'm taking that fraction out, I'm pulling it out of both of the x terms, the x squared term and the x term. All right, that's the completing of the square part that's a little bit complex is we look at the middle term, which is here, and we take half of it. So we're going to look at half of 25 over 2. So that'll be 25 over 4. And we're going to square that and add it in here. So we're going to add in 25 over 4 squared. Again, we took half of the middle term, squared it, and added it in to get this perfect square inside the parentheses. But we can't just add a number in without balancing it out. So I've got to look at the overall effect of these two numbers multiplied together. In the examples that we were doing before, we would put the same number on either side of the equation. In this case, we're going to put everything on the right side. So the net effect I have here is negative 2 times 25 multiplied by 25 squared over 4 squared, right? Let's figure out what that value is. Let's grab a calculator. Bear with me for a minute. And I'm getting a negative 25 over 8. Just double check that. So I think I'm going to add 25 over 8 here to balance this out. I figured out that it's a negative 25 over 8 that got added in overall net in the parentheses, so I have to add that into the outside to balance everything out. All right. So that coefficient is still sticking around on the front here. And then when I collapse this into a perfect square, the half of that middle term that I took is what ends up being inside the parentheses. So it's going to be 25 over 4. And this is the perfect square that we end up with. And then combining those two numbers on the outside, we get 65 over 8. All right. Let's just think about this for a second in terms of a graph transformation. This number on the front is going to be a reflection, right? Because it's got a negative sign in front of it. It's going to be a vertical shrink. because it's a fraction. This is going to move everything to the right, and this is going to shift everything up. So if we think about moving everything to the right and moving everything up, what ends up happening, this is a parabola faced upside down because that that first term is negative. When we move over to the right like this, and we move up a certain distance, that actually gets us to that maximum point or the vertex. We'll talk about this in the next video. So the maximum height is actually going to occur right here at 65/8. We'll talk about in the next video how we use this type of equation to think about the maximum value, or the maximum value of a parabola, or the minimum in the reverse. So we think that the maximum height for this will be at about 8.125. Are we in? Yeah, we're in feet. So that is the answer to part A. We used completing the square to find the maximum height of the ball. In the next video, we'll find an easier way actually to get that we don't have to use completing the square, where we'll just use the axis of symmetry. For the second part, we want to find the horizontal distance that the ball has traveled. And if I think about this whole trajectory as a parabola, there are two places where the graph is going to cross this sort of fake x-axis that I've made. And one is going to be way back here, and one is going to be here. This one we kind of reject because it has to do with before time starts. Time is starting right here, right? This is when time is equal to 0. And that's actually going to be a negative number. And so we would reject that anyways because we can't have a ball traveling a negative distance. So the quadratic formula gives us the zeros, or the x-intercepts of the equation. So we're going to use the quadratic formula to solve part B. Our original equation was negative 2/25x squared. Let's go back and look real fast. Plus x plus 5. And we're solving this equal to 0 when we're finding those intercepts. So this is A. B is going to be 1. And this is going to be C, right? So we'll do x is going to be negative b, so that'll be negative 1, plus or minus b squared, that'll be 1, minus 4 times a times c, and the whole thing over 2 times a. All right, grab your calculators, plug that in. We only need to plug in the positive value right here. We're only going to do the positive because the negative is going to be that 1, 0 that we were rejecting that was before time started. So when you plug this in, just do the positive value. And you should get approximately 16.3 feet. So that's saying that back here at this picture, that the distance that the ball is traveling from that guy to where it hits the ground, that's going to be about 16.3 feet. All right, that was a nice challenge. I will see you in class. Thanks for watching.